In this tutorial, what we're going to do is take a look at how we can convert a flowchart into some nice GenieBASIC, which is a slightly better way of controlling your projects. And once you make some more sophisticated things, you'll need to be able to do this. So what I've got here to start me off as a sort of foundation is my flowchart that I made in the previous tutorial. And what we're going to do is we're going to convert this automatically into BASIC, which kind of helps quite a lot. To do that, what I do is I click on Project. I then go down to Microcontroller. And there's an option here that says Convert to Basic. This is what the basic version of my program looks like, and what we can do straight away is to try and smarten this up to make it a little bit more convenient for human beings to read. Let's look at the code and commands that we've got. The first command in any GenieBASIC program is the start command, and this simply gives us a point from which to begin our program. So this is where we're going to start, which is at the top. What we can do in our program is we can build various different labels, which are sort of like landmarks that we can use in our program. Now, the basic program here calls them label 1, label 2, label 3 by default. I'm actually going to change this and I'm going to call this main, because it's the main part of my program. If I do that though, what I also need to make sure of is that all these things here are called main as well. So let's just take a second, make a quick rename. Normally, in text editors, you can go Control and H, and you can automatically do all of these. Unfortunately, the Circuit Wizard thing doesn't support that. Okay. And this one here as well. Like so. Okay, so let's take a moment and actually look at what's being done. The first thing we do after start is we say, right, here's a new landmark, and we call that main. The next thing we do is we say, we do the little diamond decision block basically. We say that if input 3 is currently set to 0, so if it's not currently being pushed, then what we do is we go back to main. So if we hadn't pushed the button when the program first started and we got to here, then we'd come here, there's main, and the first thing we do is we'd ask that same question again and again and again and again. If, however, it's the case that that's not what's happened, then what will happen, so if the button has been pushed down, then we'll turn on the pattern of lights to show us the number 1. And what we'll then do is we'll ask the question about that button. If they let go of it yet, if they have let go of it, we have to go back up to the top, otherwise we can carry on and we can show a number 3, a 4, a 5 and a 6. Let's just pause for a second and look at how this output thing here is written. We use the command out to indicate we want to alter an output, then we put a percentage, and then we put some X's, some zeros, some ones. Let's look at what it actually refers to. In this particular Genie chip, if you remember back on our flowchart, when it was running, we could actually have this view of all the digital inputs and outputs, which are just here. This represents all the different pins on the Genie chip, and you can see here that we've got output 0, output 1, output 2, output 3 we didn't use, but we did use number 4. The same idea applies in our BASIC. This represents output number 0, output 1, output 2, output 3 we don't use, and that's output 4. We don't use 5, 6 and 7 either in this particular one. So if I just wanted to turn on output 0, I put a 1 there. If I just wanted to turn on output 1, I put a 1 there. If I wanted both 1 and 0, I set these 2's to 1's, and so on and so on and so on. And that's how it works. So what else can we do to smarten this up a little bit more? Most proper programmers tend to use indentation, and by that we mean all this space that we've got just here, and they're writing their programs to help them see what's going on. So while the GenieBASIC wizard does a fairly good job, it's a little bit sort of unattractive in the way it sets out our code. So what we're going to try and do is to reduce how far in the page that sticks. And we can do that by highlighting all the text like I just did there with our mouse. I actually use the keyboard, but with the mouse, and holding down the Shift key and pushing the Tab key. The Tab key is the one that normally, if you're writing an essay, would indent the text at the start of a paragraph. So hold down Shift and push the Tab key, and that pulls back that text. Another thing that we can do, which is a slightly better way to write our code, is to smarten it up a little bit like this. We could actually say, if input 3 is 0, then, and we'll put this line here on the next line, indent that some more, because that's inside an if statement, and actually use this idea of else instead. This is a very powerful programming concept. Like this. Let's take a look at my reworded code that I've just done. I've said, if input 3 is 0, so if we haven't pushed the button, then we're going to go over to main, and we're going to start the process all over again. If, on the other hand, input 3 is 1, because it's only 0 or 1, it can't be 2, 3 or 4. If it's anything else, then what we do is we show that number 1, and that's the end of that if statement. I could have multiple lines in here. I could put some extra commands in this section here, but as it happens I'm only using 1. So we can actually reformat all that text, look a bit more presentable by doing that. And again, a professional programmer who wrote their own code from scratch would, if they were getting paid for anything to do it, would most certainly be expected to set their work out like this. So you can go through and you can do that. Let's look at one more idea we could do as well, because wouldn't it be really nice if we could have a sort of an animation to try and make the dice look like it's being rolled. If we actually made this in real life and we pushed this onto a Genie chip, then what you'd actually see is you'd just see all 7 little LEDs flicker on and off, and it wouldn't really look like anything. If we could make our own proper animation to sort of make it look like maybe the 2 dots that you get when you've got a 2 and the 2 dots that you've got when you're making a 4, if we could make those 2 alternate, that would look quite nice. And then we took a finger off, it could show us the number that we wanted. We could do something like that. Let's look at a way we can use some more labels as well to try and smarten our code up a little bit more. What if, as well as that main label, what if I had a nice label for something called 1, and if we had a label for something called 2, 3, 4, 5, and 6, and I was able to use those. Let's look at how we can use this. We know that this here is the number 1, so I'm going to cut that code out. I'm going to paste that under here. We know that this bit here is what a 2 looks like. Put that in there. And while I'm at it, I'll just quickly do the 3 and the 4 as well. Okay, so what we've now done is our code's a lot longer. It's also a lot tidier as well. And we've got this idea of 1, 2, 3, 4, 5, and 6. So I guess what we want to be able to do is to say that if we are currently pushing the button, then we need to go and find this little thing here. We actually call these subroutines when they're set out like this. We need to go down here, find 1, display 1, and then come back up and carry on again. So if we want the code to go to that subroutine, we use a command called go sub 1, and that's going to send the basics, going to send what's called the pointer or whatever you'd like to call it down here, and that's going to turn the number 1. Once it's done that, we need it to return back to where it came from, just like we do with the others. Like so. We need that to do that in all cases. So it's going to show us the number 1, and it's going to return back to where it came from, at which point it then carries on. So we're going to do this for all of our code. Go to 2. Copy and paste here to speed this up. So we've got 1, 2, 3, 4, 5, spell it correctly, 6. 1, 2, 3, 4, 5, 6. Good. For some reason, it looks like I missed one just there. That's okay. So 1, 2, 3, 4, 5, and 6. And those are going to go 1, 2, 3, 4, 5, 6 and send us back. Let's have a quick run of our code just to make sure it still works, because we've made a lot of changes. So at the moment, you can see what's happening here. The code's just going to slow it down a little bit. A bit more than that. There we are. So it keeps coming back to main. The button hasn't been pushed down, so it keeps sending it back up to main up there and coming through. So let's push that button down and hold it down. So that's showing 1, showing 2, showing 3, showing 4, 5, and 6, and it goes back to the top again and repeats through. And as soon as I take my finger off that button, which I just did a second ago, I've upset it a bit now. Hang on, I'll do it from here. Yeah, as soon as I take my finger off that button, it should stop on whichever one it was on before, And let's have a look what number I was on. That's the dot, 2 dots, that's the 4, that's a 6. I've rolled a 6 just there. Look at those outputs, that looks pretty good. So that seems to work still pretty well. The problem I've still got, when we look at this on my circuit diagram and we run it, is when that's running, even though it looks quite a pretty pattern at the moment, that's not how it looked when it's run in real life. It'll just make all the LEDs just look very, very dim, but they're turning on and off so fast. So what we might want to do is to try and revise this just a little bit and see what else we can add to it. Another thing I'd like to look at before we do too much more is to look over here on the left hand side of the screen. You'll notice we've got this little green line that's been about 1/3 filled up, and this indicates how much of the memory on the chip that we're using up. So at the moment we're using about 1/4 of it, so we could have 4 times this amount of code and still fit it onto that tiny little chip, so we can afford to keep going.